Hello and welcome to the presentation on shaft-induced voltage for VFD motors. First of all, this presentation is pre-recorded, and as that is the case, it's a little bit different for me. I'd much rather be doing this in person, so this is going to be a little nerve-wracking for me. It's okay. I'd like to thank Ray Burt, ACG, and CxEnergy for the opportunity to make this presentation, as well as their staff. A little bit about me. Tom Hedrick, professional engineer. I actually graduated from Duke University with a BS in electrical engineering and 1981. So to let you know, give you some perspective, that was Coach K's first year at Duke. And in his time since then, he's only won over 1,100 games and 5 national championships. So every time I think I've accomplished something, I look at Coach K. I also graduated from Wake Forest with an MBA in operations. But most of all, and you need to understand this, I am by nature a redneck. I grew up on a dirt road in North Carolina and adjacent to the family farm as well. So during this presentation, I will definitely probably get red-faced. I will probably start to sweat. I will definitely use incorrect verb tense and mostly a lot of words that you may or may not understand because I've probably made it up. But in spite of all that, I am here to shed a little bit of light on shaft voltage and what I've learned over the years. And this pre-recorded message should get started right now. If for some reason I mess up, since this is recorded, I will not stop. I will keep right on going. So for right now, let's get started with our presentation. Thank you, thank you. Everybody be seated, please. I appreciate it. We got to get this redneck on the road. All right. I know. It'll be okay. Thank you. Shaft voltage. The standard AIA message to make sure that we're doing everything in compliance with continuing education. And of course, the copyrighted material by our company, International Commissioning Engineers, better known as ICE. This course description presentation will focus on the shaft voltage that is induced from a variable frequency drive, the main causes of the induced voltages, the magnitude of the problems, and possible solutions for this issue that reduces life expectancy for VFD motors. The presentation is supported by peer-reviewed research, field testing, and performance-based solutions. In the presentation, you will see case study measurements, documentation, and analysis. Audience will walk away with information on how to prevent damaging shaft voltage on bearings in the motor in order to reduce maintenance issue and capital cost expenditures. Our objectives for today: number one, identify causes of damaging shaft voltage in the VFD motor applications. Number two, identify methods to measure the shaft voltage in the field. Number three, identify possible solutions to mitigate shaft voltage and extend life expectancies of VFD motors. And number four, determine proper language that can be included in standard specifications for future projects. So let's get started. As a precursor to all the presentations I do, it is electrical in nature, and as such, there are dangers in electricity that need to be fully understood. Damaging and fires can often occur, so only qualified people should be doing field measurements and this type of testing. This was me during a test at my house that I wasn't using proper techniques for. What do the experts say concerning this? Well, industry applications said that pulse width modulation inverters have recently been found to be a major cause of motor bearing failure in inverter drive systems. The surface of bearing races with operation greater than 500 hours are melted several times at the whole surface due to small craters. And finally, on Journal of Electrostatics, the statistical model of electrostatic discharge and bearing of induction motors that are fed by an inverter causes EDM, electrical discharge machining, bearing currents that have been found to be the main cause of premature. In fact, in other industries, it's said that up to 90% of all motor failures that are driven by VFD are the result of this type of bearing failure. Lots of times, maintenance folks, they just go out there and know that a motor's burn up. That's pretty much the extent. And for that reason, they want to get things back up and going. So what do? They take that motor off, they put a new motor in, hit the start button, get it back going, because that's their charge to keep things going. But if we really look at what caused the failure, and that's what we're talking about today, we'll find that 90% of those are the result of this type of bearing failure. The bearing failures themselves, this is actually a bearing that has been cut open, and we're actually looking at the raceway. You'll notice, and we'll talk about this a little bit later, the fluting washboard type effect that's caused. That's actually as a result of the frequency, each flute based on the frequency we're operating, where the bearing has suffered discharge voltages that cause the damages along the way. This is what it looks like on the inside if you actually open it up and take a look. These studies and white papers will come away with all types of reasons for the failure, what we're talking about. They actually have concluded this one, bearing currents in their relationship to PWM drives show that there are frequencies less than the natural frequency of zero sequence system impedance. The capacitance divided the voltage and yield the following algebraic equation. If you were to take a look at the equations in this, they're about 12 variables long. Now, those variables will tell us the individual components that make up this type of induced shaft voltage. But let's just break it down. A lot of time we don't care necessarily what causes it. Can we fix it? Leave the smart folks to doing the equations. But the following things can be reasons to cause that. Number one, the VFD location, the actual location of the drive in relationship to the motor being driven can cause additional effects. The frequencies at which the carrier frequency at which the VFD is operated, the motor size, as we have found, larger motor size, the more prevalent it is to find this type of shaft voltage. The actual calibration of the VFD. Have we gone through the setup, auto-tune function or tuning functions to make sure that it's set up right? Is it properly grounded? Do we have any interference? Do we have, in particular case, standing waveforms that can be developed at particular frequencies that should be edited out? All those go into this 12 variable equation and spits out an answer of the probability of the voltage that is induced on the shaft. What we want to know is, do we have it and can we get rid of it? That's what's important to us today. Bearing failures are costly. As we can see here, typical motor from 30 horsepower, 300 and 500 up. Obviously, the larger the motor, the more expensive it is. The higher the repair, anywhere from $1,500 to $20,000. The downtime can be even more catastrophic. If we were, say, example, I'm going to show in a field operation where HVAC was on a continuous running research, and if that particular motor failed, they would end up shutting down an entire research project that's been ongoing for 2 years. You can't replace that. Those are valuable. How do we get away from that? The actual cost of the motor failure itself total with the operation time from $8,000 to $140,000, and that can seem extreme, but in a lot of cases that's very prevalent. The cost of putting a voltage reduction device in, minuscule savings for preventing one motor failure, anywhere from 94 to 98% of the total cost. Sources of bearing failure. As we discussed before, we got multiple inputs that can cause it, but what actually is happening at the motor itself? Well, we have capacitive EDM current from the VFD. The capacitive induced voltage from pulse width modulating systems will produce an actual voltage onto the drive itself, onto all motors. That's this one up here. Anywhere from, starting at 1 horsepower, fractional horsepower, all the way up to 500 horsepower and above. At higher horsepowers, 100 horsepower and up, we also see the cumulative effect of high-frequency circulating current from the VFD. High-frequency circulating currents may flow due to a high-frequency flux produced in the common mode. That's in larger horsepower motors. Smaller motors, we get the capacitive effects. What do those do to us? Well, let's talk about what it doesn't do. If we were to go just with a standard motor, off-the-shelf motor, and apply across the line, strictly line voltage, on balanced input, we usually have no problem with those motors. Typical 460 volt going in, we got 3-phase currents. They are essentially balanced. Electrical induction motors are designed for operation on 3-phase sine wave power, either 50 or 60 hertz. The input power is balanced in frequency phase, 120 degrees apart in amplitude, and the common mode voltage, the sum of all 3 phases, usually equals about 0 when properly balanced. Note, bearing protection is generally not needed except on large frames motors. So straight across the line, you're just running the motor at 460 volts, 208 volt, 240 volt, 3-phase, you don't have a problem. But let's put a variable frequency drive on this. Our pulse width modulated voltage can be a problem for the bearings, and that's caused in the common mode voltage condition. When operated by a VFD, the power to the motor is a series of positive and negative pulses that are sent. The input voltage is never balanced because the voltage is either 0 volts, positive or negative, with rapid switching between pulses in all 3 phases. Common mode voltage is usually a square wave or a 6-step voltage waveform. In other words, we're taking the standard wave, we're converting it to a DC, on a DC bus, and then we're chopping the wave up and giving it amplitudes so that we can produce a waveform that simulates a sine wave. In other words, that motor is used to seeing that sine wave, but we use fast switching and different step functions in order to produce a waveform. You can see this one up here, and you can see it can be a choppy waveform at that. Bearing protection is needed to mitigate electrical discharge machining damage in these bearings. Capacitive ED current. An electric motor works like a capacitor. This is the issue. How does the voltage get induced to the shaft? Well, the pulses to the motor from the VFD create a capacitively coupled common mode voltage on the motor shaft. In other words, we've got a shaft that is just sitting there, and then we got the rotor and the stator, which between them, when it's not matched properly, will produce a capacitance voltage, and that capacitive voltage gets induced onto the shaft itself. Voltages are measurable with a shaft voltage tester and specially designed shaft voltage probes that can make contact with the spinning shaft. So let me demonstrate this or from an information standpoint. The shaft, which is turning at whatever frequency you need to meet the load requirements, that shaft itself, if you go from the shaft to the motor housing ground or to a proper grounded system, you can measure voltages being induced on that shaft through this capacitive effect. Now, those voltages want to get to zero. It wants to get back and dissipate. But how does it happen? These voltages actually arc through the bearing. Electrical discharge machining creates thousands of pits. The bearings degrade, resulting in increased friction and noise. Eventually, the rolling elements can cause fluting damage to the bearing races. As a result of that fluting will cause bumpy aspects into the race of the bearing itself. Lubrication grease can deteriorate and get burnt. And its potential for the unplanned downtime that we discussed. You can see here burnt grease, you can see the little pits, and you can see the fluting. We'll look at those a little bit closer. How do you test for the shaft voltage? If you have a shaft voltage tester, a digital oscilloscope essentially, with up to 100 megahertz bandwidth, or a good meter itself that has some oscilloscope type characteristics to it, then you can measure these shaft voltages along the way. You need something that measures on the tip, a contact that you can put onto the shaft itself, and you need a wiring back to a ground to be able to test that. And you need something obviously to hold that in place, because obviously you got rotating machinery. You don't want to be doing that where there's a problem with possible damage. EDM discharge waveform. What does the waveform actually look like? If you notice here, this is a measurement using that oscilloscope as we discussed. High peak-to-peak common mode voltages, typically from 20 to 120 volts peak-to-peak, from top to bottom. When the high-speed oscilloscope is set up to capture the discharge waveform, one can see the common mode voltage increasing normally, and when the discharge threshold is reached, the high frequency discharge occurs and an current arc through the bearing to the ground. In other words, we're producing a voltage, an increasing voltage in the shaft as it's going up. When it gets high enough to discharge, in other words, the voltage can jump across from one part of the bearing, from the shaft through the bearing, and go to ground. When it can reach that critical discharge point, that's when you get an arc. And that's when you get these particular pits that occur in the race of the bearing. These voltages reach a level sufficient to overcome the dielectric properties of the bearing grease. They discharge along the path of least resistance, typically the motor bearings, through to the motor housing. Grease as a dielectric is not very good. In fact, most common grease that's installed in bearings is only good for 0.4 volts of dielectric strength. In other words, any voltage on that shaft higher than 0.4 volts, and remember we said that these voltages can get from 20 to 120 volts, so obviously over 0.4 volts. At that point, you've gone over the discharge or dielectric constant of the grease itself, and an arc can flow across that. When that event happens, temperatures are extremely hot to melt bearing, hot enough to melt bearing steel and severely damage bearing lubrication. In other words, burn the grease and pit into the race. During virtually every VFD switching cycle, induced shaft voltages discharge from the motor shaft to the frame via bearings, leaving a small fusion crater in the bearing race. In other words, this isn't happening every once in a while. This is happening every single cycle. Hundreds thousands. Depending on high frequency, it can happen a million times and cause these little pits. Frosting and fluting in the bearing race. These discharges are so frequent, millions of an hour, that before long the entire bearing race becomes marked with countless pits known as frosting. That frosting are the little pits inside the bearing race. And that actually, this top frosted bearing race is the blow up of a particular flute in the outer bearing race itself. Phenomenon known as fluting may occur as well, producing washboard-like ridges across the frosted bearing race. Fluting causes excessive noise, vibration, and heating, ventilation, and air conditioning systems. It is magnified and transmitted through the duct. So you can start to hear, and I've been in the presence of these hundreds of times. What happens is it starts to rumble or roar, kind of like there's something wrong. You don't know if it's caused by the motor. You don't know if it's caused by the drive, the fan, whatever. You just hear that noise, and as you get closer, you can determine it's happening in the motor, and if you vary the speed, you determine that it is louder and more intense at higher speeds. When bearings fail, we can cut and inspect, and this is how we have done it ourselves, as well as we've seen the results of other field tests that we've seen. I'm not saying that you would have to do this. I'm just saying this is a result. When we had something fail, if you take the bearing, the motor's failed. You know there's a problem. So if you take the bearings and you cut them open, just slice them open like we've seen, you will see grease that is burnt. And then you'll start to see frosting and fluting along the way. You look for the evidence of EDM in the bearing race and ball itself. Actually, I didn't mention this earlier, but the ball will develop pits and damage as well. So now you did have a nice round smooth ball. Now you've got a ball with pits and damages in it, so obviously that gets to be a problem as well. EDM are millions of microscopic electrical pits created when the current discharges. The individual pit is usually between 5 and 10 microns, small, but over time enough to cause you damage and freeze up. Bearing failure, is it a problem worth saving? Regardless of the type of bearing or race damage that occurs, the resulting motor failure can cost thousands, even tens of thousands of dollars if it's in production. Failure rates can vary on many factors, some of the ones we discussed, but evidence suggests that a significant portion of failures occur only 3 to 12 months after a startup. I have seen this as well. If it's intense enough, if it develops a voltage wave arc that's 20 volts and higher, then you've got less than 12 months before you end up with a bearing failure as a result of motor failure as well. Because of today's AC motors have sealed bearings to keep out dirt and other contaminants, the electrical damage has become the most common cause of bearing failure in AC motors with VFDs. Remember, I said some estimates have it as high as 90% of all motor failures. They're bearing failures, but those bearings seize and cause you to lose your motor. High-frequency circulating currents. Not only do we have the EDM, but in larger motors, 100 horsepower and up, high-frequency currents may flow due to the flux produced by the common mode in kilohertz or megahertz frequencies, usually present in motors above 100 horsepower, and they circulate through the motor bearings to the shaft, to the frame. And you can see this curve along there. Capacitive just increases almost linearly with the motor size itself. The high frequency current increases in an exponential type form, and those two are additive effects. So both of them together produce really difficult bearing currents that can cause you problems. voltage discharge in attached equipment and gearboxes. Well, would be common to understand if we've got a voltage on the shaft, it also connects to driven pieces of equipment that usually can have bearings associated with them or be attached to direct drive, which means that voltage there will find a place to discharge as well. So you could end up with damaging driven equipment as well as the motor. Along with the high frequency currents, you may also have capacitive EDM currents, which travel down the shaft to the attached equipment. What we need to do is come up with a method, and how do we divert that voltage to ground so that we don't get damage with these arcing currents. Shaft mitigation methods. There are 6 common ways to get rid of this issue, solve it. Number 1, insulated bearings. So you can take and use insulated bearings, not just sealed bearings. That's not what I'm talking about. Insulated bearings, where the insulating material along with non-conductive resin or ceramic layer isolates the bearings and prevents shaft current from discharging through the bearing to the frame. In other words, now it's still inducing the shaft voltage, but because we've got these insulating bearings, it does not have a way to arc over and cause damage in the bearings. So it just sits there with the shaft voltage. That is more prevalent if you go with a larger and larger motor, which you may have. You will see that insulated bearings can be rather expensive to install. It's a good system, but it can get to be expensive. Ceramic bearings. The use of non-conductive ceramic balls prevents the discharge of shaft current through this type of bearing. Once again, we have shaft voltage we have produced on the outer race bearing, but it doesn't have a way to arc over because the ball itself is made out of a non-conductive material. Once again, still leaves a shaft voltage there, but it doesn't have a path to ground through a damaging arc current. Number 3, conductive grease. In theory, because this grease contains conductive particles, it would provide a low impedance path through the bearing, which would bleed off the shaft current through the bearing without damaging discharge. In other words, you're essentially hooking a jumper across the bearing so that any shaft voltage jumps over and goes directly to ground. You don't have the buildup of voltage and the arc over, it just bleeds off to ground. In theory. Once again, if it's not kept lubricated properly, then that particular type of grease can overheat and you can still end up with the damage. A grounding brush. The first grounding brush that I personally saw was in 1981. Worked at R.J. Reynolds Tobacco Company, later at M&M Mars. Early VFD motors. They were huge. And it was for a water source pump, and that particular motor had an extended shaft, and on that extended shaft we had a graphite shoe that was attached to the shaft through a spring mechanism and then connected to ground. So early on, that was my first experience with a shaft voltage. It would bleed to ground, and with the old early VFD motors that did not have the switching capacity that we have now, and it was just block step current, you could get some pretty hefty voltages. Once you did that, it would bleed all of that off. Does it work? Yes. The problem with that, extended shaft, you have to do the maintenance on the graphite, but does it work? Absolutely. Number 5, bearing protection ring, or SGR shaft grounding ring. Rings specially designed engineered conductive microfibers to redirect the shaft current, provide a reliable, low impedance path from shaft to frame, bypassing the motor bearings entirely. Once again, here we've got tied to the shaft itself, those fibers are on the ring or on the shaft, and they're actually tied to the motor housing, and that provides a path to bleed off any induced voltage. Number 6, a Faraday shield. This shield prevents VFD current from being induced onto the shaft by effectively blocking it with a capacitive barrier between the stator and the rotor. Certainly an effective way. You've eliminated any ability for the capacitive effect that we need using this Faraday shield. Expensive way to do it. Does it work? Absolutely. Using the spring energized brush, like I had said, my first introduction to that, they can have fast wear, maintenance needs due to high friction. Conventional single point contact with a carbon block, I said graphite, carbon, graphite, but you can see the shaft on a blown up is not really as smooth, and neither is the pad itself. So over time, it can wear, and you have to stay on top of that maintenance-wise. SRV, shaft voltage reduction device, same thing, SGR, shaft grounding ring. Usually zero friction and wear, proprietary nano-gap conductive fiber, which runs along the shaft itself and provides a path to short circuit any shaft voltage directly to ground. These provide 100% circumference microfiber contact and designed for high frequency VFD voltages from 10 kilohertz to 100 megahertz. These other shafts, just to call it out, generally designed for DC type current. Best practices. Out of all the ones we look at, if I were to say what's the best practice, remember 6 different ways. The best practice would be use this SBR device for a protection ring that is at this point right here. And we'll see they can be internal to the motor or external faceplate, and those fibers rub the shaft the entire time. Usually it's good to put a colloidal silver on the surface, and that silver, as we know, silver is a very conductive metal. That silver just provides a smooth and highly conductive surface for the actual ring itself to provide the ground path. Install an SBR device, bearing protection ring on the drive end of the motor for capacitive EDM current, and stop the high frequency circulating currents by insulating the non-drive end bearing of the motor itself. In other words, using insulated bearings just on the non-drive end of the motor. This practice will protect both the motor drive, end bearing, and attached equipment. So you're looking at how do we get rid of it? This is a terrific way to do it. High frequency ground path from the motor. Now also realize that you need, remember I said back in the beginning, improperly grounded systems where you don't have the VFD, the motor, and the conductors all tied to a common ground. But remember, we've got high frequency signals, high frequency voltage doing this. And understanding that, you need a superior grounding system from the motor housing to the common ground that you would need. So some people use a high frequency ground strap from the base of the motor down to the facility ground. It is a braided cable used to lower the impedance between the motor's frame and earth, secure one end to the motor, the other to earth ground, and then they're back to the VFD. And it isn't aggravated by high frequencies. The SBR device, there are patented devices that are out there. This is just showing up close the fibers around the shaft. It's completely around the shaft all the time. This channel comes up where the fibers provide the path to the channel of the ring, and the ring is attached to the frame of the motor, and then a path to ground. Before and after shaft voltage. Over here on your left is a problem. Remember back when we saw the buildup of voltage in that shaft on every single cycle? It peaks and then it quickly discharges down to zero. That's the point at which we get the arc. And then on the opposite part of the wave, the negative sequence, then it also arcs and goes to zero on that one, every single cycle. With the solution, with a shaft voltage SBR device installed, then you look at the voltage and it's essentially zero. You might have a little tick every once in a while where the shaft voltage, where it was induced, but then it quickly bleeds off, providing a great solution with no damage to the bearings or to the motor. The device itself, if you're using this particular type of device, remember I said it could be on the exterior of the shaft, close to the driven equipment, or there are more and more motor manufacturers now that are providing this as an option, where you can get the motor with the shaft voltage reduction ring installed inside the motor directly, so you don't have to worry about contractors or your maintenance staff or anyone having to install that. It's already installed and comes part of the motor itself. The device installation internal, like I said, it's inside the bearing retainer ring and next to the rotor, pre-installed. You can get this shaft protection, preparation, and ring installation using silver shaft coating while installing the device to enhance the shaft conductivity and prevent oxidation. Variable frequency drives and electrical bearing damage. Bearing currents in motors operated by variable frequency drive can cause premature or catastrophic failures. High energy pulses with extremely fast rise times, DVDT discharge in the motor bearings, can cause electrical discharge machining, EDM, damage to the race and the rolling elements, the balls. And the motors need bearing protection with the SBR device, best practice, installed on the motor. Attached equipment and gearboxes need that protection as well. If you put it on the motor internally or at the drive end attached to the frame, that will protect the driven equipment and gearbox. As we had said earlier, one of our reasons, things you want to walk away with is the specifications. This has to be included with the motor itself in the motor specs. Typically, section 2305.13, motors, general requirements, shaft grounding. All motors operated on variable frequency drives need to be equipped with a maintenance-free conductive microfiber shaft ring with a minimum 2 rows circumference microfibers to discharge any voltages. Now that's using what we call the best practices. If you want to use something other than that, there are plenty of manufacturers and equipment that can provide you with the language. What I wanted to point out here is that it needs to be included in the motor specifications. High frequency bonding, remember we talked about for larger motors, absolutely. 100 horsepower and above, we need to include that grounding strap because we're going to have those induced high frequency voltages as well. Case studies. Okay, take a deep breath. Here we go. These are actually case studies that I was involved in and what we saw in the field, the measurements I used, and then what we did to mitigate the issues. ICE, with the assistance from the controls group, took measurements using a Fluke power quality meter, in other words, capable of oscilloscope type characteristics, on pump motors. Now these pump motors themselves were at a large pumping station for a university. In other words, we were, in these particular cases, we were looking at 250, 500, and 700 horsepower motors, large motors in this case. As follow-up for motor failures, these measurements were taken. Pumps 1, 2, and 3. Shaft voltages demonstrated why ICE would conclude the motor bearings for VFD motors will fail prior to expected life. Without insulated bearings, ground rings, or grounding brushes taken into account, the dielectric capacity of the bearing grease is approximately 400 millivolts. Remember, 0.4 volts for the grease itself. That would deteriorate with high enough voltages. The path through the bearings is available and would arc. If we included insulating bearings, the path through the bearings is not available, and without a shaft grounding ring or brushes, these voltages remain on the shaft. The voltages are induced onto the motor shaft due to the inherent nature of the VFD motor fields. Number 2, pump 1 was operating at temperatures above 250 degrees Fahrenheit. That was measuring the outside of the motor housing itself. Extremely warm, and when we checked into, it was starting to make some noise. The pump did not operate, we did not operate pump 1 for extensive amount of time to achieve those temperatures due to, number 1, shaft voltages and bearing noise. So we just ran that long enough to get the readings. Voltage readings were taken from each motor shaft to the main motor housing ground, with the VFD operating at between 30 and 51 hertz. We stopped at 51 hertz because that was the maximum based on the calculations for what it was going to be used. So in other words, we were measuring exactly what the pump was going to be doing in real world. I was concerned that proper auto-tuning and parameters were not installed during the VFD startup, so we had those particular parameters retuned, and we still come up with the measurements. These are the actual measurements that we saw. In this particular case, this motor ended up being a rebuilt motor operating at 50 to 85% of the speed. It shows the shaft voltage operating at approximately 12.8 and 24 volts AC with an operating frequency of approximately 320 hertz at 50% of the undetermined frequency at 85%. So this particular was at 50%, and you can see the voltage peak to peak was anywhere from 12 volts up to approximately 20 volts, and this was just when the motor was installed. It hadn't even been used for a very long time. We caught this one early as a means. The rebuilt motor was installed. We were called in after the one motor had already failed, and they ended up rebuilding the motor and putting it back in. So this is basically a new motor, and we're already getting these types of voltages. Once we installed the shaft voltage grounding rings, then it dissipated to just a few, actually millivolts in that case, but essentially zero. Problem solved. Number 2, HVAC supply motor VFD case. This was a motor, university, where it was between 30 and 50 horsepower is what it was used for. And this particular motor, we can see that even with 6.7 milliseconds per division, it's essentially solid line. In other words, this thing was, the frequency at which it was operating and the discharges into the shaft were incredible. We estimated this motor was going to last about 3 months. That's it. It had already deteriorated to that point. Even though the voltages were only about 12 to 13 volts, 26 volts peak to peak, it was so, this motor had been operating for about a year to 2 years. it was already into the point where it was going to be damaged and fail, starting to make some noise at this particular point. For this one, the university just, it had dual motors, so you could switch one to the other so that you can continue operation for their research projects. So we were able to get in. They replaced it with a shaft grounding ring, and problem solved. This concludes our actual presentation. I hope that you've had an opportunity to learn a little bit more about shaft voltage, the impact that it has on motors and motor failures, and how we can keep from doing that. It's a very successful method. I've been doing this field work for 42 years, and like I said, I first was introduced to it in 1981, and I have tried to preach the message of on VFDs, we've got to ground those shafts. Just as a note, that's not me, but that's not a Photoshop picture. That's a picture of one of our extremist guys, field guys, engineers who actually went to the South Pole and used our flag and took this picture. I don't do that. Thank you. This concludes it. If they've got any questions, you can see my information there, my cell phone and my email. Please feel free to contact me at any point. Thank you, and thank you for your attention.